it to be engaging, so definitely ask questions. I'll be checking the chat frequently. Actually, if you want to stop me in the presentation, I think that's fine too, but it is being recorded, so it will be available as well. So I encourage lots of questions. I was invited here today to talk about what I know best, which is avoiding manufacturing defects. And so there's a lot of basics and then there's very detailed specifics. I'll cover the whole thing. And if you have questions, please ask me. You know, just as a high level concept, PCBs are literally the backbone of electronics. So I know that a lot of people are focused on chip manufacturing and chip design. You can't forget about the system and the system design and the PCBs. Those are also critical to a good product. So we're going to cover manufacturing because I know manufacturing. And these are some of the topics. So the number one area where you can have a PCB defect is in the plated hole wall. Okay, so this is where all the failure modes are likely to occur, or very often they do occur. These are the serious failure modes, serious defects where if you're building an airplane, you know, the electronics can fail. Or you're building a self-driving car, the electronics can fail. You don't want that to happen. So having a very well-designed board from vias is really critical. And then there's all sorts of other issues that can happen, and so those will be talked about as well, especially plating and etching. How do you prevent these defects from happening is from design rules, following the right design rules. So that's what this presentation is about, and we'll just go one by one through it. And again, ask questions if anything comes to mind. But the first thing that every designer, PCB designer, really needs to dive into is what's called annular ring. So the question is, what is the final hole size I want? And what is the minimum pad size copper feature that I need in order to give me the required annular ring? So if you look at the picture, the one on the left has a little bit more annular ring and the one on the right has very little annular ring, or we call that tangency or no annular ring. According to IPC class 2, you can also break out of the pad. So your drilled hole can actually fall outside of the pad, and that's called breakout. And so that's acceptable to class 2. So understand what kind of board you're designing for. What's the application? If it's a military, aerospace, you know, life-based application, maybe you need to consider a class 3 design rules. So if you consider class 3 does not allow for tangency or breakout. And so when you defect as a manufacturer, what we do is we ask the customer, you the designer, to either reduce your final hole size or increase the pad size. So it's always good to talk to your manufacturer and understand what are the pad size requirements for that drill hole size. At Sierra Circuits, we're okay with about a 5 mil annular ring to achieve no breakout. And the more your design allows for, the better. So if you have space to have a 20 mil pad and an 8 mil via, let's say, or a 10 mil via, please go ahead and do that. The bigger the annular ring, the more robust the design and more people can manufacture it. Okay? So along with annular ring comes this concept of drill to copper that we'll talk about that a little later. And also with holes comes the concept of aspect ratio. So aspect ratio, I'd like to talk about that. Once you drill your whole wall, it's not necessary that you can plate your hole, right? And so drilling the hole is just part of the process. Now you have to plate the hole. And if your board, your total board dimension is really thick and your drill is very thin, you're going to have an issue with getting the plating solution into the via. And so that is, let's say, a high aspect ratio and can cause a problem. So you want to keep your aspect ratio about 10:1, meaning if you're drilling an 8 mil or a 10 mil via, you don't want more than 100 mil thick board. Very quickly, you can add teardrops to your design. Those will help with breakout. Some very important, but I would say nuanced scenarios that can cause defects are copper slivers. So when we're building the board, if there's any, let's say, very tiny copper islands, there's always a risk that the resist will come off of those copper islands and cause, a plating defect. So be careful about that. Next is the solder mask dams. So the purpose of solder mask is to cover the copper, so the copper is not exposed and doesn't oxidize. And second, to provide dams for the solder paste in assembly so that solder bridging doesn't occur. So you want to have a solder mask dam to help with the assembly part of the process. Some PCB fabricators will open up all of your solder mask dams if it doesn't meet their design rules, which completely eliminates the purpose of a solder mask dam. Because for a PCB, you don't need it. But in order to assemble the PCB, you do need it. You should have it. So here in this diagram, we're depicting a 5 mil solder mask web. We can go easily down to 4 mils and maybe even smaller if you have a high technology requirement. But solder mask is extremely important. One option is, as a designer, you can send your solder mask layer that matches 1-to-1 with your copper layer. And if you do that, the onus is on the PCB manufacturer to increase the solder mask openings around your copper features according to their design rules. So that's absolutely okay. And I would just leave a note in your README saying that you'd like the manufacturer to open up the solder mask for you. If you have a very tight, high technology design, I would not leave it up to the fabricator. I would very clearly specify your solder mask layer and the following the right design rules at the same time. So you'd have to talk to your fabricator and understand what kind of solder mask, let's say, feature sizes they can hold. And the issue in manufacturing, of course, is that if their solder mask becomes too thin, the feature becomes too thin, it can lift off of the panel, basically causing a defect. So understand from your fabricator what they're capable of doing. Another big topic I think it's important to know is when you're designing your stack up, what kind of materials and copper weights you're going to be using. You have to take into account not just the electrical properties of the material and the control impedance structures you're going to be doing, but also is your stack up a balanced construction. If you don't do a balanced construction, you can end up with warpage, which basically means that you don't have a flat circuit board anymore to assemble onto. which makes it very difficult to assemble onto, and you can have defects in assembly. Or it may not fit in your connectors or slots, or, it's basically a mechanical issue at that point. So on the left, you see an example of an unbalanced construction where layers 4, 5 are thicker copper than layers 2, 3. Instead, what you want is what's on the right, which all of your inner copper layers to be similar in value and copper thickness. If you don't do the right side and you do the left side, you have this chance of the bowing or the warpage that might occur. Another big kind of topic is managing heat. If you have an application that is very heat intensive, there are a couple of things you can do. The first one is you pick a better, more robust material. The second thing is I've seen customers do is instead of solder mask, they use flex material as a replacement to the solder mask, because flex material has better electrical properties. And so knowing the application, knowing what kind of heat's going to be generated, you can pick the right PCB material in your stack up. And of course, best practices, place your components properly, making sure that you have enough space between the components. In this case, we're talking about heat, but you also need to space your components properly so you can test them okay, and get to your critical nets in order to probe and find out everything's okay. So component placement is always a key part of doing your design. And if you do have extreme heat requirements, you can have a metal backed board, or you could have a metal or aluminum core built into the stack up. So you can think about that, think about if you have a very kind of high-end application, how you can use aluminum or copper to suck the heat out of the board. So again, in this diagram, we're looking at basically the inside of the vias, and it goes back to drilling, and it goes back, this failure mode can go back to drilling, and also the type of material or the quality of the material that you're using. So basically, if you can imagine a whole wall on the left and a whole wall on the right, copper can grow in between the hole walls over time. And so this is called the calving issue. Now, if you're in a space type of application, at the time of drilling the via, those kind of fractures in the PCB materials called whiskers, there's only a certain thickness or length allowed for aerospace because of this specific problem of cap. Because they've seen that if you have a little bit more microfractures during drilling, and the copper plates inside those microfractures, that you can have over time a higher probability of calf growth. So knowing that this is a potential failure, you don't want your holes too close together. I would use a rule of 10 mils apart wherever possible. And you want to make sure that you get a cross-section report from your fabricator so you know, okay, did they do a good job in drilling and plating my vias? These are some of the things that we talked about in order to avoid calf. Now going on to silkscreen. Silkscreen is actually can be considered a defect. So especially if you're have silkscreen on the pad, that can impact the solder joint and the reliability of the solder joint. So what we do in engineering and PCB is we clip back the silkscreen away from the pad. And sometimes if you clip it too much, now the AOI machine in assembly can't read the silkscreen information. Maybe we lost the pin 1 marking, and maybe it's not clear, what's the location of that, let's say, component. So you have to be careful with properly aligning your silkscreen and following the manufacturing rules and the keep out for a silkscreen. So talked about, kind of orientation already and making sure we have a good, clear pin 1 marking. Silkscreen is usually done not through screening anymore per se, but also kind of like a direct write type of printer, like a big inkjet printer. So you get a little bit more accurate silkscreen with that. I think the point here is that when you're designing your ground copper cores, be very careful about that. You don't want any copper right up to the edge of the board. So when you route your board, there's an issue. Going through copper, you don't really want that unless you have castellated edges, in which case you have to follow the guidelines for the design guidelines for castellated edges. So you want a good understanding of your ground and power and keeping that away from the edge of the board. For us, a routing tolerance is plus or minus 5 mils, and I would say most fabricators have a plus or minus 10 mil routing tolerance. So I would definitely follow those guidelines that your fabricator has for route tolerance and keep the copper from the edge of the board. So, and this slide kind of talks about all the tolerances that you should be aware of in manufacturing your board. So another one is when we plate the via, we would like a plus or minus 3 mils in terms of the finished hole size after the plating. So if you say you want a 10 mil finished hole, we would actually drill it at probably 13 mils, plate the hole, and it would shrink back down to 10 mils. And in that process, we would want a tolerance. So if you have a critical requirement where you're going to be putting in through hole components into those vias, we need to know about it. You need to say it on the drawing. You need to call out the tolerance in that manner, saying, this hole cannot be any smaller than, this size. So that's a key requirement. And sometimes when you have a press fit connector, I've seen customers call it a plus or minus 2 mil tolerance, which is absolutely okay. It alerts us there's a special hole to consider. Other tolerances are the etching tolerances, right? So if you have a 5 mil trace versus a 3 mil trace, the 3 mil trace will probably have more variation after etching than the 5 mil trace. So be aware of that, especially if you have any high speed nets and you're concerned with any sort of attenuation or reflections. Just be aware that there is always these tolerances in etching. So speaking of tolerances, for characteristic impedance, we like plus or minus 10%, and we can go down to plus or minus 5%, and that's with what's called a first article, where we basically run your board design completely through the shop to measure out all the tolerances that have happened, and we make adjustments. And then the second time we run it, we're going to have a tighter tolerance on the characteristic impedance, because what makes up characteristic impedance is the quality of the etching, the accuracy of the etching, which you can adjust by edge comp and thickness of the copper. Also the thickness of the dielectric material, let's say to a reference plane, which can be adjusted by picking different glass styles and prepregs, as well as understanding the temperature press cycle that you need to go through. So basically understanding press out thickness of materials and tolerances of the etch traces. Those are the key things that drive characteristic impedance. So in terms of assembly, you can avoid issues such as tombstoning if you double check that the footprint that you have on your board matches the part number or the MPN that we're going to procure or that you procured. You want to make sure that those footprints match. And then also you want to make sure that you have a good stencil file that basically tells the assembly facility how much solder is required for that component. So if you have too much component or bad solder paste accuracy and deposition, you can have all these sorts of issues. But in order, from a designer's perspective, the way you control this is designing your pads properly and then also designing your solder paste layer properly. So in short, this is like a summary of the different checks that we have. The biggest one that I haven't really dived into too much, but I'd like to mention is the plated through hole to copper clearance, or also known as drill to copper. That's a super critical design rule, and not all designers check for that before they send us their designs. The reason why it's a little hard to check for is because of the way we build boards. You first have to enlarge your vias, then run your drill to copper check, because that's the size of the drill we're going to be drilling. And when you send us your designs, it's really a finished drill size. So that's why it kind of gets missed sometimes, which is okay. That's why we're here, and that's why we do our checks. The only other kind of critical check here that I think is important is, really getting your drill file in line with your drill table in your fab drawing, and making sure you don't have like double hits in your drill file, making sure that your drills aren't too close together for all the reasons we talked about before. Signal checks, I think most people do a great job when running their design tools to find any kind of signal layer issues. This is our summary of our capabilities. So, we can go up to higher copper weights like 4 ounces, even 6 ounces in some case. We can make very thin boards like 10 mil thick, 14 mil thick, as well as thick boards like 250 mils thick. Sorry, I'm speaking in mils, but so, these are the parameters that we have based on our equipment, and not every fabricator has the same equipment. So their rules might be different. So it's important to understand what are they comfortable in manufacturing as well. And, as an example, we have a small drill bit of, 5.9 mils. And it's not just that you can drill that hole with accuracy. In order to do that, you need a vision drill system. It's also, can you plate that via, can you clean that via and then plate it so there's no hole wall defects. So kind of what I talked about and alluded to earlier. So taking one of these capabilities and assuming it to be 100%, you can follow that and there's no issues, is not the right way to go. Some of these design rules play off of each other. Like, for example, if you have heavy copper, it's going to be harder for us to etch through it. So we need, more spacing between the traces in order to etch a 4 ounce copper board than, let's say, a 1 ounce copper board. So your minimum tracing space in a heavy copper board is different than your minimum tracing space in a standard copper board. So all these are very common design rules that play off of each other and are important to know. When it gets really kind of difficult and hairy is when you have laser drilled microvias, you have impedance structures, you're trying to hit a certain characteristic impedance, and your board is very dense. So your microvia has to be small. Therefore, in order to have the proper aspect ratio for plating that microvia, that determines the thickness of the dielectric, which impacts your impedance, characteristic impedance calculations. So that's when it gets hairy, and all these design rules really do play off of each other, and you have to really kind of work with your fabricator to get it right. So that is a quick kind of rundown of what I think are some critical design for manufacturing guidelines to keep in mind when you're designing your board. And we also have a very in-depth DFM guide on our website that's free to download. It goes into what I talked about in much more detail, and explains a few other concepts in manufacturing as well. But if anyone has any questions, I welcome them at this time.
All right, thank you very much, Amit. I have one question. There was a day I submitted a project to a PCB house, and the price was just to the moon. It was so much. So I remember sending them an email trying to ask about what are some of the things that goes into the pricing of the board. So as you are an expert in that, I know the board size matters, but apart from the board size, what other things should be considered to reduce the cost of the board?
Okay, great question. So in order to reduce the cost of your board, I'm going to change the question a little bit and say, what shouldn't you do to increase the cost of your board? So the things that increase the price, so everyone has a minimum lot charge. Every fabricator has that. So you can't really get away from that. Some fabricators will have a certain minimum lot charge, and other fabricators in more expensive areas of the world will have a different lot charge. And that's just the basic fixed costs to run their facility for all the equipment and the people and the salaries, and making sure that you have the quality controls in place. So if you don't have stringent quality controls required, then maybe you don't need to go to a facility that has high fixed costs, because that's not your requirement. So I would say that goes in the first selection of your board. But understand that if you do have quality requirements, that if you go to a lower cost facility, right away you are going to get a different level of quality of product. So second, in your design, I would say the number one thing is to minimize the number of vias that you use in your design. Vias are one of the most expensive parts of your PCB, because drill bits cannot be used more than a certain number of times, and then you have to throw it away. So those drill bits are a very costly part of the manufacturing process. So minimizing the number of drills and then increasing the drill size as much as possible if your design allows it also will make sure you don't increase your cost astronomically. The drill size, if you shrink your drill size and you shrink your tracing space, those two things will drive up your cost the most. And I'm speaking in a more or less standard design rule practice. If you are in a situation where you're designing with a 0.4 millimeter BGA, you probably have to go to laser drilled microvias, in which case you want to optimize your design rules and you want to design with 4 mil tracing space and use your laser drilled microvias intelligently to increase your tracing space if you can. And that's how you would not increase your cost unexpectedly because of the 0.4 millimeter pitch.
Okay,
So
all right.
I have one last comment on the
Okay.
price increase. If you have multiple drills that start and stop on different layers, that will also be a huge cost adder. So always have, if you want to keep your cost low, always have one pad stack where the whole drill hole goes from the top all the way through the board to the bottom.
Okay, thank you very much. Yeah, I think there are some questions in the chat, so if you could address them.
Yeah, our friend Daniel has been doing a great job answering those chat questions. But I'll take a look. Let's see, one question. What's a good ratio of copper thickness to minimum spacing? I have had issues with under etch when the gap was too small for the copper thickness. So after 3 mil tracing space, I like to use just a rule of thumb, that you want an extra mil of spacing for every, let's say, well, let me say it this way. For every ounce of copper, you want 3 mils of spacing. I think that's a really general rule of thumb. So for 2 ounces of copper, you would want 6 mils of spacing. I think that kind of suffices to answer that question. There's a question about polarized components, and I'm not actually good to answer that. I think I would want this person's email and I can get them the answer. But in terms of alternative components and whether they're, let's say, form, fit, and function equivalent, we do have some tools that can help you determine that, as well as I can just get you a good answer from a component engineer. Any other questions? Okay, well, thank you very much for this opportunity to present. Is there anything else I can help you with?